So today is an exciting day because right here I have a box of supplies. It's always good when this starts with a box of stuff. So this right here is essentially a DIY electric motor kit. So this has all the parts in it that I need to build another electric motor. So we've got laser cut parts for making in this case, the front or the back of the motor. We've got laser cut sheets for making a stator or the rotor as well. These are the smaller ones. We've got an 8mm shaft. We've got a spool of copper wire, a lot of nuts and bolts, all the things we need. Also, for some reason, an Allen key. Not sure what we need that for. But anyway, let's get started building an electric motor. Now, of course, I previously made an electric motor, which I bolted onto my homemade electric skateboard. And amazingly, it was powerful enough to move the skateboard with me on it, which was super nice. But as we've seen in that previous episode, it wasn't quite powerful enough to go through off-road terrain or go up steep hills and things like that. So I wanted to make an improved version of this motor that would be powerful enough to do these things. So I went back to the drawing board and came up with a new and improved design, or well, hopefully improved, at the very least it's new. And so that's where we're at today. So before we get into assembling this new electric motor, why don't we take a look at how this one is different from the old one first, so the things that I've changed. First of all, what I haven't changed is that it's still a switched reluctance motor, so it's still the same basic principle. This also means that this new motor can be driven by the same electronic driver that I built, which was performing quite well, I think. Now, it's possible that this new motor is really good. I mean, I don't know yet, but maybe. In which case the electronic driver might become the new bottleneck, and so maybe I then have to redesign that one as well. But for now, let's not worry about that. We're going to assume the driver is not the problem. So over here I've got a bunch of laser cut parts, some of which are from the new design and some of which are from the old design. So let's start by taking a look at the old one. So this is what the stator looked like on the old motor. So it's a 12-pole stator, which has 12 coils on it, and then inside of that we used to have this 8-pole rotor, which would sit inside it like this, and then by energizing these coils in a particular sequence, you would get the rotor to spin like this, right? Now, one of the biggest problems I think with this design is how low these teeth actually are, how small they are, because that means you cannot put that much copper on them. So you can have not that many turns of copper wire. Of course, you could use a thinner wire, but then you have less current going through it, so that doesn't really get you anywhere. So there is very limited space to make good coils on this design, which limits the amount of magnetic flux that you can produce, and therefore the amount of force and ultimately torque that your motor can make. But of course, there was a reason why I did this. And that reason is that this makes the distance from the center of the motor to the air gap relatively large, which means you might not have as much force being applied, but because you have a long arm, you can still generate a reasonable amount of torque. And so this is an optimization problem. If you make a motor that has very long teeth and a small rotor, you can put lots of copper on those teeth and produce a lot of force, but the moment arm will be tiny. On the other hand, you can also make a motor like this, where you have very, very small teeth, small coils, not that much force, but you get a large moment arm in return. So the question is, where do you draw the line? Which ratio do you pick? Now in this case, I picked a very shallow slot depth, or a very small height for my teeth and my coils, but I think I made the wrong choice there, because in a motor like this, theoretically speaking at least, there is a quadratic relation between the amount of current in the coils, or the number of turns, and the amount of torque that the motor produces. So theoretically speaking, if you double the number of turns, or double the electric current, you can get 4 times as much torque. And so that is more dominant compared to the size of the moment arm, which is a linear thing. If you make the moment arm double the size, you get double the torque, not 4 times. So the length of the teeth, theoretically at least, is more dominant, is more important than the length of the moment arm. And so I should have gone with a much smaller rotor and much larger teeth. Theoretically, right? Of course, there is all kinds of other things that are at play here, so it's not quite as simple as just make the teeth ridiculously large and use a super tiny rotor. But I did think that this ratio was not right, so I changed it. So in the new design, it looks like this. So the teeth are much longer than they used to be, at like about 2 times or even 2.5 times the original height. I think it's like it's about 2.2 times. I'm not sure. It's much bigger at least. Also, what I've done is I've made the teeth slightly thinner, and I've got these little bits sticking out at the end, which helps keep the wire on the tooth. Let's see if the camera focuses on this. It doesn't. Basically, it's going to make it much easier to wind coils on these teeth without the wire sort of falling off every time. Also, I've actually kept the size of the rotor exactly the same. You can see the old rotor still fits in here pretty much perfectly, like this, because I thought about making the motor the same size and just changing the ratio, what I just talked about. But then I thought to myself, getting all this stuff laser cut is pretty expensive. It better be right this time, or at least it better be a lot better than last time. And so I decided I would just make it a bit bigger, just in case as well, right? Just in case, make it a little bit bigger as well. So I've actually just made it bigger on the outside and kept the rotor size the same. So in theory, we should now have much more force because these teeth are much bigger, so we could put much more copper on there. But also, we still have the same moment arm because we still have the same rotor size. So there is no sacrifice there. What I have done, though, is I've changed the thickness of the back iron. So the steel that sits on the outside here is a lot thinner on this new design than it used to be. And that's because if you look at the path of the magnetic flux in the stator, the back iron has to handle only half as much magnetic flux as each one of these teeth. So, theoretically speaking, you can make the back iron half the thickness of the teeth, which is what I've done here, and I hadn't done that on the old one. On the old one, I was just like, well, let's just make sure it's thick enough, right? On this one, I've really made it as thin as theoretically possible. So even though we've got significantly longer teeth, the size of the motor as a whole hasn't increased all that much, which is quite nice. What I've also done is I've made a new rotor. So this is the new rotor. It's very similar to the old one, except it's ever so slightly bigger, so that the air gap between the teeth here and the teeth on this one is slightly smaller. It's still not quite as small as it could be. I think it's like 0.5 millimeter now, and it used to be like 0.75 millimeters on the old one. It's not great, but it's better, and it should make a difference in the amount of torque we can produce as well. Also, there are some mechanical considerations about the air gap. I'll get into that in a minute. What I've also done is I've cut away a lot of extra metal that we don't need. So the old rotor was just basically a solid block like this, and the new one has a lot of extra metal removed, which makes it a lot lighter, because you don't need all this metal for the basically for the same reasons we just talked about with the back iron on the stator. It's the same thing here. You don't need to fill up the whole thing. One thing that's a little bit tricky though is on the old rotor I had these extra holes to put threaded bars through it to clamp it all together. On this one we're going to have to rely purely on glue for the whole thing to stick together, so let's hope that works. Also, I'm going to make the new motor a little bit shorter than the old one. I think the old one was 64 millimeters, or at least the lamination stack was 64 millimeters. It's now going to be 55, I think. So it's going to be a little bit shorter. And And apart from just trying to make it shorter, which puts less mechanical load on whatever you mount it to, I've also done this because it should make it easier to deal with the smaller air gap, because if you have a longer motor, it's more easy if the shaft is slightly like this or slightly like that for it to start rubbing on one side. If you have a shorter motor, the risk of that happening is lower. Also, to make sure that we can get away with the smaller air gap, on the previous motor I built the front and the back of the motor myself in the shed. I just grinded them out of a sheet of steel and drilled the holes myself. For now I decided, because of the smaller air gap, we need better tolerances. So I got the front and the back of the motor laser cut as well. It looks like this. And so they both consist of 2 sheets. One of them has a slightly bigger hole, and the other one has a slightly smaller hole. And so they go together like this. And then I can take my bearings, which I have in this bag. There we go. Little ball bearing. The bearing can slot right in there, like this. And so that should give us very good positioning of the rotor shaft, and therefore hopefully make sure that despite the smaller air gap, there isn't going to be any rubbing in this motor. Okay, so there it is, the basics of the new motor design. If there is anything I forgot to mention, I guess you'll hear it along the way. I think it's time we start building this thing. Okay, so here is a big pile of metal sheets which we need to glue together to make the rotor and the stator of our motor. Now, I've already prepped these by filing and sanding off all the rough edges, which the laser cutting company actually offers to do as a service, but that costs extra money, so I decided to do it myself. It was a bit of a pain. It took me like 3 or 4 hours, I think, but it's done now, so we can start gluing things together. So why don't we start off with the rotor first. So the process is very straightforward. We just take one of these discs, put some glue on it, take another one, and stick them together like this. And then we just keep going until we get through the whole pile. So I'm just going to make sure to cover each sheet nicely and make sure there's glue everywhere before I stick them together, because we want there to be as little electrical contact between these sheets as possible, right? That will give us best performance and minimal eddy current losses. Now, it isn't a disaster if there is some electrical contact in some places. You just want to make sure it happens as little as possible. Okay, so just grab another sheet. There we go. Right. Alright, so now let's put this aside and leave it to dry so we can start building the stator. Right, so that is all of the layers glued together. So now what we need to do is wait for this to cure, I think for about 24 hours. And then we can start on what is probably the most difficult part of this project, which is going to be winding the coils. So on camera it'll look like I'm just about ready to start winding the coils on this stator. In reality, I've already done a number of attempts and I ran into some problems. So first of all, I started winding with copper wire that was 0.75 millimeters in diameter, the same wire I used on the previous motor, and then I realized that on this one I probably have plenty of space to use 1 millimeter wire instead. So I undid all of that. And I got myself a spool of 1 millimeter copper wire, which, you know, handles quite a bit more current because it's actually like double the surface area. Also, I had an issue where the coating on the copper wire would get damaged by sharp edges on the steel core, and I've tried a number of different things. At the moment, what I've done is I've filed all of the sharp edges, at least the ones that I could feel. I filed them off, and now I'm just going to stick some bits of paper on here, and hopefully that's going to be sufficient to solve this problem. So maybe I can now finally start actually winding this thing. So each one of these coils has 30 turns. On the old motor I used 16 turns per coil, so we have almost twice as many turns, which, if you do the maths, should result, theoretically speaking, in roughly 4 times as much torque. On top of that, of course, the wire gauge is much thicker as well, so the cross-section of this wire is like 2 times as much, so we should be able to also run much more electric current before we burn it up. But I'm not really planning to run this at anything significantly more current than the old one, so I think we're still going to be using about the same maximum current. So considering all that, we should expect about 4 times as much torque from this new motor. Of course, one should also keep in mind that this new motor is a little bit shorter than the old one. Like half a centimeter shorter, so maybe it's not going to be 4 times, more like 3.5 times. Regardless of that though, I'd be super happy already if it's got 2 times as much torque as the old one. Like, of course that would already be a massive improvement. Something that might also make a difference is the air gap size. So because I'm trying to build this new thing with better manufacturing tolerances, if you can call it that, we should be able to have a slightly smaller air gap than before, which should also increase the torque. But I don't know how much smaller of an air gap we will end up getting, and so it's very difficult to predict how that will affect the torque output of the motor for now. But yeah, if the air gap is significantly smaller than on the old motor, we might also get an extra boost in torque from that, which would be very nice. So with the stator and the rotor prepared, it's time to make the front and back of the motor. So as I mentioned before, we're going to make those out of these pre-cut pieces of steel. So there is one with a bigger hole, one with a smaller hole, and now we just need to put them together like this so that our ball bearings will be able to sit in here, which will eventually support the shaft that this rotor will sit on. Why do I have 5 pieces? I ordered 4, I think. Okay, well, I guess 5 it is. So while that paint is drying, we can start working on the rotor. So of course this is the lamination stack that we made earlier. And what I have here is an 8mm shaft, which is going to have to go through this hole. And then we're going to put these bearings on the shaft as well, and these clips to keep them in place. So the first thing we need to do is grind a flat side on this shaft so it'll fit through this D-shaped hole. It's the wrong size, you see that? You know, I'm not a mechanical engineer, right? So you have to cut me some slack here. Okay, so new plan. I think we're just going to try without the clips on the shaft. We're just going to put the bearings on because that should be a very snug fit and that should keep the rotor in position anyway. Also, of course, the magnetic field is going to assist in centering the rotor, so even if it tends to drift off in some direction, it should get pulled back into the center by the magnetic field from the stator. And if all that doesn't, turns out not to be enough to keep it centered, we can always buy the correct clips later on and add them in, right? So, but for now, we're just going to try and get away with only the bearings. Now, before we put the motor together, I would like to make the output shaft thinner first. So, on the electric skateboard, which is what I want to use this motor for, the pulley that I'm using on the motor shaft has a 6mm hole in it. So, I need the shaft to be 6mm thick rather than 8, so I'm going to have to grind this down, which is easier to do now that this is not in the motor yet. So what I've done here is I've built sort of an improvised lathe, which is a drill in a drill stand, which is in a vise, and so that way we can spin the rotor, and then using the grinder we can grind this down to, well, 6mm. Now what we need to do is get this rotor in here, like that, and then we need to put the front and back side of the motor on that we just made. So it seems to fit pretty well. Of course, we're only going to be sure once we put the other side on as well, but for now, that starts to look like a proper electric motor. Right, let's get the other side. So I've done a little bit of fine tuning, like adjusting all of these nuts to get everything perfectly aligned, and I think we're good. I mean, look at this. That's running quite smoothly. There is like the tiniest bit of rubbing going on in there. I mean, I don't know if you can hear this on the camera microphone, but of course there's a bunch of motorbikes going by when I do this, but yeah, you can barely hear it. It's very, very quiet. I think it's just a little blob of glue left on the inside of the stator, and it should take care of itself once we get the motor up and running. So, I mean, yeah, there it is, right? The new electric motor. I think it looks pretty cool, actually. I'm just gonna have to tie these wires together, make that a little bit neater as well. Now, there is one kind of dumb mistake that I made while making this thing, which is that I forgot to drill the holes in the front to actually mount it onto the electric skateboard or onto the test bench that I've made. But this is where that extra part comes in that I also had, which we can use to make like an adapter plate. So I'm just going to drill some holes in this one instead so that this can be mounted onto the test bench or the skateboard, and then using these holes in the corners we can attach it to the motor. So I consider that problem solved as well. Alright then, so the electric motor is now fully assembled, the switched reluctance motor Mark III, and I have to say I'm very, very happy with how this turned out, at least mechanically of course, because really we haven't tested it yet. Speaking of which, originally this video was going to be one big video from building the motor all the way to testing it and then putting it on the skateboard. But I realized that this is taking longer than I expected, and I haven't uploaded a single thing for like super long, so I've decided that this is just going to be part one. Right? I hate to be the guy who does that, like the big multi-part things, but I also don't like keeping everyone waiting for a stupid long amount of time when I've already got quite a bit of video on the building process of this thing, which I think is pretty interesting on its own. So in part two, it's going to be all about testing this machine and finding out if its performance is any better than the previous version. I mean, hopefully it will. I will say this, if it performs half as well as it looks, I'm going to be perfectly satisfied. Anyway, that's it for today's video. If you've enjoyed it, maybe consider clicking the like button or even subscribing to this channel. And of course, thank you very much for watching.